midas can be used to perform analysis and design on these type of bridges. So I'm going to be talking about the overview of Midas Civil. I'm going to tell you what is the scope of Midas Civil, in what projects you can use Midas Civil. Then we are going to talk about the different type of modeling features available in Midas Civil, the different boundary conditions that are available in Midas Civil that you can use, the different type of loads that you can apply, and how you can interpret the analysis results. Now going ahead, first of all, let us talk about the overview of Midas Civil. What is the scope of Midas Civil? So I hope you can see on your screen now that Midas Civil is a 3D structural analysis and design software, and it is based on finite element analysis. So basically Midas Civil is a general purpose analysis software, but we have tweaked it so that it is specialized for bridges. So I would say that Midas Civil is generally used for bridge structural analysis, but apart from bridges you can use it at other type of structures too, because it's a general finite element analysis based software. Another thing that I want to tell you here is in Midas Civil we have incorporated the beam theory and the 3D finite element analysis, where we model the shell and the solid elements, is also incorporated in Midas Civil. So beam theory, in which we represent the entire cross section as a point or the entire beam as a line, is incorporated in Midas Civil, and the 3D finite element analysis can also be done. Now talking about the structure types in which Midas Civil can be used, here you can see you can use Midas Civil for all type of bridges. So when it comes to bridges, you can use Midas Civil for any type of bridge: conventional bridge, girder bridge, the composite precast girder bridge, or the steel composite bridge. You can use Midas for these type of bridges, and these are the type of bridges that I'm going to be demonstrating in front of you today. Also you can use Midas for staged, post-tensioning, segmental construction. You can use Midas for those type of bridges too, and you can also use Midas Civil for cable bridges. When it comes to railway bridges, in which you can if you want to perform rail structure interaction, that is also available in Midas Civil. You can also use Midas Civil for underground structures such as subway or purification plants. If you want to perform soil structure interaction in Midas Civil, you can do that. You can also do seismic analysis. Now there are certain other type of analysis that in some project we might use, such as computational fluid dynamic analysis for suspension bridges or cable stayed bridges, and for that Midas Civil would not be the software that you would use. We have another software known as Midas FEA, which is generally used for detailed finite element analysis and analysis like fatigue analysis or computational fluid dynamic analysis. So Midas Civil will not help you there, but we can provide you with another software that can fulfill your needs. So if you are designing a cable stayed bridge, let's say, you can use Midas Civil for the superstructure analysis and design, but when it comes to the computational fluid dynamic analysis, you can take the cross section from Midas Civil to Midas FEA, and then you can perform computational fluid dynamic analysis there. So that being said, now let's talk about what type of analysis Midas Civil supports. So apart from performing static analysis, linear static analysis, Midas Civil can perform moving load analysis, which is the gist of any bridge design. You can perform construction stage analysis. You can consider the creep and shrinkage behavior of concrete, as well as how the elastic modulus of concrete is achieved with time in construction stage analysis. So it's a construction stage analysis in 3D, and you can also consider the time aspect, so you can say it's a 4D analysis. You can also perform P delta analysis, buckling analysis, eigenvalue analysis, heat of hydration analysis, geometric nonlinear analysis, material nonlinear, pushover, time history, and response spectrum analysis. So basically Midas provides you with all sorts of analysis. A standard finite element analysis software is supposed to provide for bridges, as well as it gives you a little more. Now going ahead, let's talk about the type of elements that Midas Civil is equipped with. So in Midas Civil you can model 1D elements, which can be beam, trusses, hook, cable, compression only member, gap. You can also model 2D elements such as plate, plane stress element, plane strain element, or axisymmetric element, and you can also model the 3D finite elements in terms of solid, which can be 4-node, 6-node, or 8-node solids. So now let's get started with the training. I have already set up the platform of Midas Civil. I have told you what type of bridges Midas Civil can handle and what is the ideology of finite element analysis in Midas Civil. Now I'm going to show you the graphical user interface of Midas Civil. To show that, let me just take you to Midas Civil itself and let me show you what Midas Civil is all about when it comes to graphical user interface. So I'm going to open Midas Civil in front of you and I'm going to show you the different elements of graphical user interface. Now this is how the graphical user interface of Midas Civil looks like. When you double click on the icon of Midas Civil, this window pops up, and if you have put in the right authentication, license authentication here, you can go to File, New Project, and it's gonna open a new project for you. So right now it's a blank project. You can see nothing on the screen. So this is the menu bar of Midas Civil. This is a ribbon menu bar. If you want to define any structure type, you can define it here. Node elements, all functions associated with node and elements can be defined here. Properties can be defined here. Boundaries can be defined here, and then you can define the loads here. So this way you can use this ribbon menu to define any elements or boundaries or loads. Also, if you don't want to go into this hassle, you can just right click in the model view and you will see the same options here. So you don't have to drag your mouse here and there in the screen. You can just, when you are doing the modeling, you can use anything from here. On the left hand side here, this is the works tree, and this is one of the most important aspect of Midas Civil. We'll talk about it as we go along. And on the bottom here, you see here message window written. This is an important item in Midas Civil because it is an interaction of the user with the software. So when I will create the model, when I run the analysis, if there is something wrong, the warnings, the errors are shown in this message window itself. So this is the graphical user interface of Midas Civil. I don't want to talk much about it right now because when we create the model, you will get to know how this particular user interface will be used. Okay, so to do the modeling of any structure in Midas Civil, especially bridges, we have certain bridge wizards that can help you. And the bridge wizards can be used for beams, trusses, or higher standard bridges like bridges constructed using span by span construction, balance cantilever bridges, suspension bridges, cable bridges. So we have wizards that can ease your life. They can model the bridge in front of you in no time. So now let me take you to these wizards and let me show you what these wizards are all about. So if you want to model the bridge using the standard wizards that we have in our software, you can go to the structure menu here and you can see all the wizards are listed under the wizard option here. So when I go to the base structure, I can go to beam, let's say. Let me change the unit system. I'll go to tools, unit system. I'll change the unit system to feet and kips. Now if I want to model a single beam, I can go to base structures, beam, and let's say it's a 20 feet long beam. I am defining the distance as 10 at 2, which implies there would be 10 elements, each having a length of 2 feet. So the entire length of the girder or the beam would be 20 feet. The reason why I'm dividing the beam into 10 separate segments is because we are performing finite element analysis. So we need smaller elements. The smaller the element, the better the result. So that's why I'm dividing it into 10. I'll click on add and I'll specify any cross section and material onto it. I'll click on OK, and here you can see the beam has been modeled. Now if I want to change the viewpoint here, I can change it from the dynamic view control here. This is the side view, this is the top view, and this is the cross section view. So you can change the view type from here. We'll talk about it more when we do the actual bridge modeling. Now this is one way of modeling this particular beam. If I want to, let's say, model a bridge constructed using span by span approach. So what I can do here is I can define the number of spans that I have, then I can define the cross section. If I want to put in my own cross section from AutoCAD, or if I want to define any other cross section, I can go to type 2 and I can define my own cross section. And then I can go to the tendon tab and I can define the typical tendon profile, and once I click on OK, this bridge will be modeled for you. So this is how you can use the wizards. Now let's talk about a very simple wizard, the reinforced concrete slab bridge wizard. This is how it looks like. You specify what is the span, what is the skew, if it is curved, check on the radius and define the curve. Then how the transverse, how it looks like transversely, and what are the different loads that you want to put in the model. And once you click on OK, you can see here that this particular slab bridge has been modeled for you. So it's so quick. When you are using the wizard based modeling, it creates the finite element model for you very quickly, and you don't have to worry about the integrity of finite element modeling here. It's done, everything is done automatically. So this is one way of creating models in Midas Civil. Now let's see the other way. The second way of creating the model in Midas Civil is importing anything from AutoCAD. I know for sure that when you do the general alignment drawings, then you know the alignment of the bridge. That alignment can be imported in Midas Civil using the DXF import. So let me show you how the DXF import can be done in Midas Civil. So if you want to import MicroStation or DXF files, go to File, Import, and either go to AutoCAD file or MicroStation file. So let's say I go to AutoCAD DXF. Then I can browse the DXF file, and all the layers that you have in the DXF file will be shown here, and you can import any layer that you want to import. So this way the import function can help you. So this is the second way of creating the model in Midas Civil. So the first way was to use the wizard, the second way is to import the DXF file. And when you are importing the DXF files, you have to, there are certain standard rules that you have to follow. So these are the rules that I have listed out for you. If you have a polyline in DXF file, it will be imported as a beam element. If you have surface, it's going to be imported as a plate element. But if you have a polyline rectangle like this, if I just close this rectangle, then it's going to be imported as plate element. And if I have a 3D face, it's going to be imported as plate element. So just make sure that if you have a closed structure like this, then you use the lines and not the polylines. Okay, so that being said, now let's see how we can define the material properties in Midas Civil. To define the material properties in Midas Civil, it's a very simple process. Just go to Properties, Material Properties, click on Add, and you can select the type of design either as steel or concrete, and you can select the code that you're working with, and all the parameters will be selected for you. And if you want to define user-defined ones, just go to user-defined and you can use the user-defined ones. So there are two types of materials, isotropic and orthotropic. You can also use orthotropic materials, but orthotropic materials only works with 3D elements like shell or solids. It does not work with beam elements. And it's not a limitation of the program. Basically, this is the ideology of finite element analysis. So orthotropic material would work with only shell elements or solid elements. Similarly, you can define the steel materials too. Now let's talk about the cross sections. So when you are modeling a bridge in Midas Civil, you open the new window of Midas Civil, you define the material first, then you define the cross section. Now to define the cross section, where you go? You go to Properties and you go to Section Properties. Now when you click on Add here, you have variety of cross sections to choose from. Now let me tell you where you should use what type of cross section. Now let's say you are doing a steel composite bridge, a steel plate girder bridge, and you want to model the cross frame. For the cross frame, it's going to be a standard rolled steel section, and you can select the rolled steel section from here. You can select the code as AISC 2010 database, and you can tap on the section name, and the section property will be taken by the program from the database. If you want to use your own user defined, you can do that too. So you have, if you want to do user defined, just go from DB to user. The value type section will be used when you want to put in your own dimensions, or when you want to bring in the section from AutoCAD. SRC tab, it is the steel reinforced concrete cross section. We have the SRC pipe pile. So if you are using the concrete filled steel tubes, you can define them here. And as you know, they have steel material as well as concrete material. The program will automatically calculate the stiffness for it. The combined sections, where you can combine two steel shapes together. Generally it would be used for truss bridges, or sometimes in the cross frames of steel bridges. Pre-stressed concrete cross sections. Now the pre-stressed concrete cross sections can be divided into two different segments. The first is the box sections, the second is the bulk T or the I cross section. So the box sections can be defined here, and if you want to define the I cross section, you just go to PSCI and put in the dimensions here. We also have the standard library from ASHTO type 1 to type 6, so you can select them, but you are not limited to using only these cross sections. You can either define your own numbers here, or you can import the cross section from AutoCAD, and once you do that, they would be saved in the library of Midas Civil to be used further. Then we have the taper tab, where you can define the tapered cross section, and finally the composite tab. Now this is one of the most important tab in Midas Civil, because it is useful to model the steel plate girder bridges as well as the precast I girder bridges. And we would be using this particular cross section today for modeling a bridge. And the good thing about this particular cross section is that it defines the stiffness of the girder and the tributary area of the deck at the same time. So this is how Midas Civil can be used for composite sections. Okay, now let me take up some questions from you guys. If you have any questions, please go ahead and type in the questions. I have a question from Derek Warner. The question is, can you build your own library of sections, that is CPCI series of pre-stressed beams? Yes, you can make your own library of cross sections in Midas Civil. You have two different items, two different ways of doing it. First is, you can go to section properties, click on add, go to composite and go to composite I. Here you can define the CPCI girder bridges, and you can define the cross sections by yourself and save them. You can save them as a text file, and they can be invoked whenever you want to use it. And secondly, if you are not satisfied with this shape, you can bring in the shape from AutoCAD and then save it, and it would be saved in the library of Midas Civil. So these are the two ways you can make your own library of cross sections in Midas Civil. If you guys have any more questions, please let me know. Okay, I have a question from Francisco Russo. The question is, how does the composite beam property handle non-composite loads such as self-weight and composite loads like live load? In Midas Civil, you can model construction stages. So that's one way of doing it. When you model the construction stages, then you can model the girder as non-composite in stage 1 and composite in stage 2. So this way, whatever load that you apply in stage 1 will be defined on the non-composite cross section, and from stage 2 onwards it becomes composite, so the live loads will be acting on the composite cross section. And definitely we are going to talk about it when we do the construction stage analysis scheme. The second way of doing it is, let me just show it to you here. When you define the loads, you can define the loads on the composite section, and you can tell the program that this load should be applied only on the non-composite section. So this way it can help you in that respect too. So you don't have to model the construction stage always. what you can do is you can specify the program that this load has to be defined only on the non-composite cross section. Okay, I have one more question from Scott here. The question is, for the composite section, how does it figure that 3n and n width concrete section? Okay, so I guess let me just go to the section properties here and let me go to composite. So here I think you are talking about the 3n and n factor. So there are two ways of considering it once again. If you want to perform construction stage analysis, then you can define the creep and shrinkage parameters, and the program will automatically consider this effect. So it will give you the creep deformation, it will reduce the modulus of elasticity, it will give you the creep deformation. But if you want to do it manually, you can define multiple modulus of elasticity, and you can define the long-term elastic modulus and shrinkage modulus in here. I hope I answered your question, Scott. Let's take two more questions. Okay, there is a question from Amzad. The question is, can you please show the material library? The question is, let me go to the material library. So when I go to material properties, I can select the ASTM steel cross section and the steel section here. So this way you can define the steel material or the concrete material. There's a question from Russell Jack. It's a very interesting question. The question is, when analyzing a composite bridge, one of the techniques is to model the negative moments as steel only and the positive moments as composite, since the area with the highest moment of inertia will attract the greatest moment. How does Midas do it? So let me reframe this question. All of us know that at the midspan, the sagging bending moment are the maximum, and at the mid support, at the location of the support, the hogging bending moments are maximum. Now at the sagging bending moment location, the tension is at the bottom, and if you talk about a steel girder bridge, the steel will take the tension. So the deck is in compression, the deck is not cracked. But when it comes to mid support, the stress changes. The compression is at the bottom and the tension is at the top. So the concrete actually cracks. So Russell wants to know how we can actually model this type of behavior in Midas Civil. It's very simple to model this behavior in Midas Civil. What we can do is, we can go to section manager and reinforcement here, and when I have the composite cross section, I'm going to show it to you later, I can check on the cracked section properties, and then the program will consider only the steel girder and the reinforcement when it computes the stiffness at the negative moment zone. So this type of scheme, this type of analysis scheme can be modeled in Midas Civil. I hope I answered your question, Russell, and I'm going to show it to you later on when we do the modeling. Let's take one more question. If another user has a custom property in his library, how can he export and how can I import in my model so that I can use his library property? It's a question from Sam Ibrahim. It's a very easy, the answer is very easy. Let me reframe the question for you guys. The question is, let's say I have defined a user defined cross section in one of my models, and I want to use this user defined cross section or material in the new model that I am creating now. So how do I import it? The easiest option is go to properties, go to material properties, and click on the import button here. Locate the location where you have saved that model, and this way you can import the material, cross section and thickness. So this is the easiest way to do it. There are certainly other ways of doing it, but this is one of the easiest. Okay, so now let's move on with the presentation and the training, and then if you guys have any questions in between, please keep punching in your questions. Now let's talk about how we can create curved elements. I have been getting this type of question from a lot of people, and there are several ways of doing it, and today in one of the examples I'm going to show you how to model the curved bridge. But before that, let us talk about how you can model curved elements. To model the curved elements in Midas Civil, we have a special button that you can use. So let me show you that button. So when you go to node element, you can go to create line elements on curve. When you click on this particular option, here you can see that you can define arc by 3 points, cubic curve, circle by 3 points, and stuff like that. And my favorite is cubic curve by 3 points. It's because I can define the reverse S curve too here. So I'll divide the curve into 50 elements. I'm going to define 4 points on the arc. So this is how I'm defining it. And I've defined these 4 coordinates, and once I click on apply, here you can see this type of a curve is automatically generated by the program and you can use this curve to model reverse S curve bridges. So when it comes to a curved bridge, this is an option that you can choose, and it not only creates the circular arcs, but it also creates the reverse S curve models for you. So this is how you can model curved elements in Midas Civil. Now let's go ahead and see what are the other techniques available to us for modeling in Midas Civil. Now here you can see an extrude element option. Now since I created this presentation, I can be a little biased to some of the functions that I really like. So this is one of the functions that I really like, and I want to talk about this function in little detail here. So there are different type of extrude options that are available in Midas Civil. The first is node to element. So here you can take a node and create an element using that node. And the second option is you can take the element, a 2D element, and create a plate. The third option is take the plate and create a solid. Now let me demonstrate these 3 options to you in the program. So this is this element that we have just created. Let's say I want to create support at 4 locations. So I am selecting these 4 nodes here, or let's say 5 nodes. So I selected all these 5 nodes here. And let's say I want to create more elements in the direction of gravity. What I'll do is I'm going to go to node element, extrude. I'm going to extrude it in the direction of gravity by whatever distance, and I'm going to hit apply. And here you can see it took the node and it created the element out of it in the specified direction. So I specify the direction and it creates the element for me. So this is how Midas actually, this function can be used to create elements. Now let's go ahead and talk about other type of extrusion scheme, which is line element to planar element. To do that, you change the extrude type to line to planar, and once again you can specify the direction. You can specify the global direction or the local direction by using these options here, and then hit apply, and this way you can see that I have modeled the shell element out of a beam element. So this is how Midas can help you to create these type of elements. And similarly, the third option is planar to solid element, where you can create solid elements starting from the planar elements. So extrude type is one of the best function in Midas Civil. I have used it in a variety of projects, and I use it in almost all type of projects. So it can be a very handy tool for you guys too. When it comes to modeling of piles, drill shafts and stuff like that, you can easily model it. So that was all about modeling in Midas Civil. Now I want to skip to supports. What type of supports Midas Civil provides. Now if I want to define support or boundaries in Midas Civil, you need to go to the boundary tab. So where is the boundary tab? It's right here in the menu. So when you go to the boundary tab, there are different type of boundaries that you can select from. but which one to use where. So I have created this PPT for you so that you would know where you can assign what type of boundaries. So first of all, if I want to apply translational restraint at any location, I can use the simple supports. I can check on these buttons, individual buttons, and it restrains that particular node in that particular direction. So we have the translational direction and we have the rotational direction. So as you can see here, this support can be applied, and I don't want to talk about it a lot because it is available in all other finite element analysis software, so I hope you are already familiar with it. Let's start from point spring supports. Now the point spring supports are used to model the non-stiff support provided by the soil. Now we all know that as we keep on adding load to the foundation, it settles, or there is a certain deformation in the foundation, and it can affect the structure, and that's why we perform settlement analysis. Now to simulate this kind of behavior, you can apply the point spring supports. There are different type of point spring supports you can specify. So basically, if you talk about the soil support in the lateral direction, it has a non-linear nature, and that type of non-linear nature can be defined by the multilinear type of spring. If you talk about an abutment which has soil in one of the faces and the other face is free, then the soil will only apply the passive support and not the active support. So in that case, you can use the compression only element. So this way, these type of point spring supports can help you. Now there are surface spring supports in Midas Civil, which is generally used to model the soil. It simulates the soil support by putting in the subgrade modulus. So let's say you are working on the bridge and it uses spread footing. So for the pier you are using spread footings. So you can specify the modulus of subgrade reaction, which can be obtained from the geotechnical engineer, and Midas will automatically generate this particular surface spring for you. We also have elastic links in Midas Civil, and I have never seen a model in which I haven't used the elastic links. So I would say that they are the most important type of boundary supports in Midas Civil. And how they are used? They can be used in a variety of manner. And the most important use, I would say, is to model the bearings. Now the bearing has a certain stiffness. You don't want to just apply a rigid connection between the pier and the girder. To simulate the bearing, this is the scheme that you should follow. So this node number 1 that I have shown here, this is the node of the girder. Node number 2 and 3 are two new nodes that I have created at the location of bearing, and node number 4 is the pier node. 5 and 6 are the two nodes that I have created just below 3 and 4, and I have connected 3 with 6, 2 with 5 using elastic links, and 1 is connected to 3 and 2 using a rigid link because it's a rigid system. They all belong to the same cross section, and 4 is connected to 5 and 6 because once again they belong to the same cross section. So this is how you can use different type of elastic links. We are going to use these type of elastic links as we go along in the model. Also, we have a special type of elastic link known as multilinear link. It is used for modeling the non-linear behavior of the ballast, and here you can see if I want to model this type of behavior of the ballast, I can define it like this in Midas Civil. We also have beam and releases in Midas Civil that are used in a variety of format. If you want to simulate a hinge at certain location, you can simulate that. If you want to, let's talk about precast girder bridge. Let me just give you a very standard example of this type of support or boundary. So in the precast girder bridge, let's say it's a simply supported precast, let's say it's a 3-span continuous precast girder bridge. So in stage 1, we install the girders of span 1. In stage 2, we install the girder of span 2. In stage 3, we install the girders of span 3. And in that stage, these 3 girders in 3 different spans are simply supported. But when the deck is casted on the top of them, when the deck hardens, then they become continuous over the support. So what I've done here is, in stage 1, I applied the beam and releases, and when the deck appears, I removed them so that now the girder become continuous. So this is how you can use it. We also have a rigid link option where you can use a certain master node and you can define certain slave nodes, and this is a perfect example where it can be used. Let's say you want to model an opening in the web of a particular element. You can model the opening like this, and you can make the beam elements away from the opening because you just want the stress distribution here and not at other locations. So you can model the beam here, and then you can connect all these nodes at one face or one cross section by using rigid links. Now there are node local axes in Midas Civil. They are very important when you are working on curved bridges. How? Let's say take the example of this particular bridge. Now if I see the left abutment, let's say I don't want to model the abutment in Midas Civil, I just want to apply the translational support or springs. So what I will do is I'm going to rotate the node local axis of these 4 nodes where I want to apply the support in the direction of the bridge so that I can effectively model an expansion bearing. If I do not apply the node local axis, then let's say I restrain X. So you will see that if I restrain X here, the bridge will be restrained not only in X but partially in Y also, because locally the girder direction is not the global X direction of the girder. So that's how you can use the node local axis. Effective width scale factor. If you want to calculate the stresses based on the effective width for the box sections, you can use it. Now let's talk about load cases, but before that let me see if you guys have any questions still here so that I can take up your questions. So there's a question by Amjad. The question is, can Midas support steel beams with concrete decks that are simply supported for dead load and continuous for live load? Yes, Amjad, Midas can do that, and I have shown you the beam and release that you can apply, and you can tell the program that for dead load use the beam and release, for the live load do not use the beam and release. So that type of boundary setup can be done in Midas. There is another question by Maggot Ibrahim. The question is, after creating the shell elements, how can you modify certain elements? Now the modification, there's a standard procedure. I mean, if you want to modify the shell element, I don't know what do you mean by modifying the shell elements. If you want to modify the geometry, then you need to delete the shell element and recreate it. But if you want to modify the thickness or the material properties, you can define a new material property and put it there. There's another question by Amjad. The question is, what are the optimum hardware and OS requirements of 3D finite element analysis? Well, any standard laptop that you get in Best Buy can be used for this type of software. We can also give you some other information, detailed information later on, but let's just move on here. There's a question from Daryl. The question is, can you demonstrate assigning properties or support conditions to a specific element? Okay, this is something that I missed. Daryl, thank you for reminding me. Now I'm gonna show you how you can assign the boundaries and supports to a particular node and element. Okay, so let's use this particular model here. If I want to apply boundary, let's say I want to apply supports, fixed support to the bottom node. So I'll go to define supports, I'll check on D all and R all. It's gonna have the fixed support at the bottom nodes, and I click on apply, and you can see the supports are applied like this. Now if I want to create the elastic links, I can go to elastic link and I can specify the stiffness, and I can tap on 2 nodes to create the elastic link. So this is how elastic links can be used. Let me just go to the modeling aspect of the bridges that I want to show it to you, and then you will be able to appreciate how the different boundaries can be applied. The load cases. Let's talk about loads now. Now in the loads, the step 1 will be to give the names of the load. And how you can give the name of the load? You can go to load, static loads, static load cases, and here you can define the load case name. Let's say self-weight. Let's say live load. So here you can define all sorts of names. So that is step 1. Here you are just assigning or defining the name of the load. You are not assigning it yet. To assign the load, there are different functions that are available in Midas Civil. The self-weight function, it will automatically define the self-weight of the model. We will see that when we do the modeling. The specified displacement of support, if you want to perform settlement analysis, you can do it here. And if you want to perform automatic settlement analysis, we have the settlement analysis option where you can specify what is the settlement at different nodes, and Midas Civil will automatically give you the worst combination out of them. You can define the beam loads. For beam loads, you can select the beams and define the beam loads. I'm going to show it to you when I do the modeling of the bridge. If you want to define the wind load, we have the uniform pressure load in Midas Civil, and this way you can apply the wind pressure and the wind load will be accounted for. And you can also define the plane loads in Midas Civil. The plane loads, to apply the pressure on the shell elements, you can either select the shell element and apply the pressure there, or what you can do is you can specify the plane load at that location. The temperature load can be specified. You can also define different type of temperature loads. To do that, you can go to load. Let me show you where it is available. It is available under load. Go to temperature pre-stress, and you have different options here. So here you can define the gradient temperature also, and if you want to define the gradient along the cross section, you can select from top and bottom how the temperature variation is done, and this way you can define temperature load. So if I want to specify this type of temperature loading, I can tell that from the top surface to, let's say, 5 feet down, the temperature changes from 20 to 0, and from 4 feet from the bottom to the bottom fiber, temperature changes from 0 to 10. The moving loads can be defined in Midas Civil. We are going to talk about the moving loads when we actually do the bridge model. So let's skip it for the moment. And hydrostatic loads can be defined using the hydrostatic load function, which is available in Midas Civil. And then you can do the load combination. You can also do automatic load combination based on different codes. So that completes the part 1 of the training today. This would give you an overall idea about what Midas Civil can do. Now I'm gonna do the modeling of 2 separate bridges in front of you, and let me give you an overview of the modeling that I'm going to be doing in front of you. So this is the second presentation that I prepared for you guys. It says Midas Civil Online Training 1. This is the first training in the series of training that we would be conducting in this year. So first of all, let's see what are the different type of finite element analysis that you can perform on bridges. So as I have already told you, you have 3 ways of creating a finite element model of a bridge. You can do solid element modeling, where you can represent the entire bridge using separate solid elements. They are 3D finite element analysis solid elements. You can also represent the entire bridge using shell elements, and the grillage modeling approach can also be done. So these are 3 different type of modeling approaches that can be applied in any finite element analysis software, including Midas Civil, and the practicality increases as you go from top to down, and accuracy increases if you go from bottom to up. So solid element modeling is the most complicated. It is the most unpractical, but it is most precise. And grillage modeling, it is a good representation of the bridge. It is not as accurate as solid element modeling, but it gives you very practical results. This is how the solid element modeling is done. You can see entire thing is represented using solid elements. Shell element, where I have modeled the entire bridge using different shell elements, and this is a steel box bridge. Now the grillage modeling approach, the one that we are going to use today, it is the most practical approach. Almost 80%, 90% of the bridge that are designed in the entire world, they use this approach to perform the design. And believe me, I've been working for finite element analysis for 4 years now, and 80% of the models that I see day to day, they are all based on grillage modeling approach. And since you guys would be starting working with Midas Civil for finite element analysis, it would be good for you to have a brief information or knowledge about this type of modeling approach. So what is grillage modeling approach? In the grillage modeling approach, we idealize the deck using a series of beam elements connected and restrained at their joints. Each element is given an equivalent bending and torsional inertia, and bending and torsional stiffness in every region of the slab or the girder are assumed to be concentrated in the nearest equivalent grillage beam. And how do we do it? This is a line sketch for you. You can see how the bridge deck looks like. It's a steel plate girder bridge, let's say, and I have created 4 longitudinal beams or girders representing the stiffness of the steel girder and the concrete deck in the longitudinal direction, and in the transverse direction we also have certain members that represent the stiffness of the deck in the transverse direction. So this entire bridge will act as a unit, but we want to discrete its response based on these line beams, and that's the grillage modeling approach. And this is how the grillage model is actually created. You divide the slab or the bridge into several small cross sections, and then you create cross section for the bridge. So I'm going to model 2 separate bridges in front of you. It would give you a brief understanding of how the model should be created in Midas Civil. The first bridge, it's a precast I-girder straight bridge, very standard 3-span structure, and I'm going to model only the geometry of the bridge, and I'm going to show you how you can do the geometric modeling. And the second bridge project that we are going to model, it's a steel plate girder bridge. It's a curved bridge. Let me show you how it looks like. This is how the curved bridge will look like. I hope you can see it now, and we are going to model this bridge. So first of all, let us start with the modeling of precast I-girder bridge. Let's start with the simple stuff, the straight girder bridge, and then we can move on to more complex type of bridge. Okay, so first of all, I need to define the cross-section properties. So I go to Properties, Section Properties, I click on Add, and I go to the composite type. It's a precast I-girder bridge, so I'm going to select the type as Composite I. But since we want to save time in this training here, I have already defined the properties for you. So here you can see I have punched in these separate dimensions that I have used for this particular project. I have also defined the diaphragm for the pier, abutments, etc. And I have also defined the deck elements. I'm going to tell you how these different cross sections will be used. But before that, let's start the modeling of the bridge. So I'm going to use the wizard for modeling. First of all, I'm going to go to Structure, Base Structure, Beam. Let me change the unit system from here to feet. So to change the unit system, go to Tools, Unit System, Feet, Kips, go to Structure, Base Structure, Beam, and define the 3-span length, 150, 160, 150. This is a very standard span length. You can specify any type of span length here. Click on Add, specify the material as concrete and the cross section as girder cross section. Click on OK, and here you can see this particular one girder is modeled. So right now we just have modeled one girder. Now let's copy this girder. To copy the girder, first go to Select Single here and create the window around the girder. It will be selected. Then go to Node Element, Translate, and I want to translate it in the Y direction. Let me go to the top view. This is the Y direction by 10 feet 3 number of times so that I can model the entire width of the bridge. Click on Apply, and here you can see the 4 girders have been created. This is the cross-section view. So this is how we create this particular superstructure. But if I show you the line beam view, if I change the view to line beam view, this is how it looks like. So there is no connection between the girders whatsoever, and to connect them in the real world as well as in the program, we will introduce the deck elements and the diaphragm. So first let's introduce the diaphragm. To create the diaphragm, I go to Node Element, Create Elements, and I select the material for the diaphragm and the cross section, and I click on Nodal Connectivity here, and I click on this node and this node, the diaphragm is created, this node and this node, the diaphragm is created. Similarly, I can create the diaphragm at the location of abutments. The diaphragm is created and the diaphragm is created here too. So this way you have provided the diaphragm at the locations, and now if I show you the line beam view, this is how it looks like. Now let's complete the grillage. To complete the grillage, what I'll do is I'm going to select this entire girder here, and I'm going to divide it into several small elements. And how do I do it? I go to node element, divide, and let's say I divide it into 50 separate elements. I click on apply. You can see 50 nodes have been created. Then select all these nodes and extrude them in the Y direction. So go to node element, extrude, and select the cross section of deck and the material of deck. Extrude it by 10 feet 3 number of times and hit apply, and here you can see the grillage is now complete. So this way you are going to model the entire superstructure, which has, in the straight bridge the superstructure will be modeled in this way. Now let me show you how individual elements look like in this particular configuration. So if I go to the 3D view, this is how the 3D view looks like, and this is how the 2D view looks like. Let us zoom in at a particular location and let us tap here. So you can see all these girders are divided into several small elements, and then when I perform the analysis, the results will be much better. Now there can be one question in your mind. The question is, how do we decide what is the distance between two cross members to represent the deck? Right now I have used it as 3 feet, but how do I know? The answer is, there is no standard technique that you can use. You just have to, the standard technique that I use is, I just divide the entire span into 50 smaller elements, and this is how I create the transverse members. So there is no standard rule, and how the results change? The results will keep getting better, but then they will start converging. So you don't have to specify the spacing as 0.1 feet. You just have to keep it between 2 feet to 3 feet to 4 feet, which is a standard spacing that we use for all type of bridges. Now I'm not gonna define the boundaries here, because I'm going to be using the other model to define the boundaries. What I'm going to do here is I'm going to define the tendons, because this is how the precast style girder bridge will be different from steel girder. Otherwise all other things are same. To define the tendon, let me first double click on the girder. All the girders are selected, and I go to view active, and here you can see now I only see the girder in this model. Now what I'll do is, and just to have a reference, I'm going to also activate the diaphragm. So I select the girder and the diaphragm of the pier so that I know where the span breaks, and I will go to load, temperature pre-stress, tendon property. So this is step 1. You need to define the tendon property. So name it, go to internal pretension tendon, define the steel material for it, and click on this button, define the strand diameter and the number of strands, and click on OK. So the tendon property is defined right now. We just have defined the tendon property. Then we will define the tendon profile. To define the tendon profile, click on tendon profile. I'm going to the top view here. I'll click on add, and I'll name it as G1 T1. So first of all, I'm going to model the hopped tendon. So I'm going to select the girder where I'm going to assign the tendon. So I selected the girder in span 1, the girder 1 of span 1, and I'm going to assign the property as tendon and input type as 3D, and I'm going to specify the location of the tendon. So it's a hop tendon. It goes down in the center of the span, and then it comes up. And you need to specify the insertion point, which can be the first point on the girder. And when I click on OK, let me show you the side view. You can see how the tendons is defined. So if I zoom in at this location, you can see the hop tendon has been defined. Now to define the bottom tendon, click on add again. I'm defining second tendon. So G1, let's say B1, the bottom tendon, and I'll select the same girder elements. And I will select 3D type, and I'm going to define the bottom tendon this time. So it's going to be at the bottom all through. So this way the bottom tendon is defined. So you can see there are two tendons in this particular girder. Now I want to define the same tendon in other girders. What I can do is I can just copy move, and I can move it by equal distance, and I can ask the program to copy it on the second girder. So this way you can copy the tendon from one girder to another girder very easily. Now let me tell you one modeling scheme here. What I generally do is, let me go to the view type as the hidden view. So generally what I do is I rename the girders so that I know from which element number the girder line starts. So what I do is I go to node element, I go to renumber girders, and I am renumbering the girder line 1 from 1000 element. So I selected girder line 1 and I select the order of preference as X. So girder line 1 has been renamed. Then I'm going to rename girder line 2 starting from node number element number 2000. So it's done. Then element number 3000 starting for girder line 3. Then element number 4000 would be the first element of girder line 4. So this way I have created the 4 girder line renumbering. And the good thing about this scheme is that if I want to copy the tendons now, I can copy it using the element increment approach, because I know I just have to increment the element by 1000. I click on OK, and here you can see the second tendon on girder 2 has been defined. So this is how you define the tendons in Midas Civil. And since you know the technique now, you can define as many tendons as you want for the precast eye girder bridge. So this completes the training for precast eye girder bridge. I just want to switch to the steel girder because it's a little more complicated, and you guys will learn a lot out of it. So now first let me give you the description of this particular bridge. So this is the geometry of the bridge. Here you can see we know what is the girder spacing in the transverse direction, 10 feet. The bridge center line, we know what is the radius, and we know what is span 1 and span 2, and we know what is the cross frame spacing. Secondly, we know, so this is how the radius will be calculated. So what I'm gonna be doing is I'm gonna create 4 nodes at the location of the girders at the origin, and then I'm gonna use the extrude feature to create the entire element. And this is how the cross frames look like. So now let me start the modeling of this bridge. It's gonna be pretty interesting, so I want you guys to focus a lot here. So let me just, so I've created a start model for you guys so that I don't waste time in creating the section properties and material properties. I already have the start model here, but if you want to know how these cross sections are defined, you just go to properties, section properties, and you can define the cross section. Now as I said earlier, I'm gonna create 4 nodes first. So I'm gonna go to node element, create nodes. I'm gonna create one at the origin, and I'll copy it 3 times in the transverse direction by 10 feet. I'm gonna hit apply, and here you can see the 4 nodes have been created. So you can see the 4 nodes here. Now I'm gonna extrude these nodes, and I'm gonna rotate them so that I can have more nodes. But what is the angle of rotation? So now let me compute the angle of rotation in front of you. so that you guys know how you can use the Excel computations for midas. So radius is 1250 feet, span 1 is 150 feet, span 2 is 180 feet. Now I want to know what is the angle subtended by span 1 at the center. How do I know it? So the total angle would be 360 degree on the circle, and the circumference will be equal to 2 multiplied by 3.14, which is pi, and the radius. So this is the entire circumference. The angle subtended by span 1 is equal to its span divided by the circumference multiplied by 360 degrees. So this is the angle subtended by span 1. The angle subtended by span 2 will be equal to the span 2 length divided by the circumference multiplied by 360 degrees. So this is the angle by span 2. Now as I said, we are performing finite element analysis. So we are going to divide the girder into several individual elements. And how do we do it? We divide it into 50, as I said earlier. Generally I use the cross frame spacing, the cross beam spacing as 3 feet. So for span 1, it's gonna be angle subtended would be this angle divided by 50. So each element will have this angle. And how do I use this angle? I go to midas civil, I select these 4 nodes, I go to extrude, and I'm gonna go to rotate type of extrude 50 times, and I'm gonna specify the angle in the clockwise direction, z-axis, and I'm gonna specify the center. And once I click on apply, you will see that the girders are created, and this is how the line beam view looks like. Now I'm gonna do the same thing for the span 2. Span 2 is 180 feet, so I'm gonna divide it into 60 elements. So for span 2, it's gonna be this angle divided by 60, which tallies with span 1 because we are keeping the cross frame spacing as 3 feet. So I'm gonna keep it as 60, the number of times here, and I'm gonna click apply. So here you can see the entire length of the bridge has been modeled. So once again I used the extrude option, and then I went to rotate. This last time I went to translate, this time I went to rotate, and this is how I created the entire girder. Okay, so the girders have been modeled now. Let's go ahead and model the cross frames or the cross bracings. And how do I do it? I go to node element, I go to create elements. So let me show you how the cross frame look like. This is how the cross frame look like. We need the C1025 cross section and the angle section for all other elements, and let me create them now. So I'm going to create them on abutment 1 first. To do that, I go to node element, create elements. I'm going to select the cross section as C1025. I'm going to click on node connectivity, and I'm going to click on this node and the last node, and this is how I've created the first member of the cross frame. Now I'm going to select this member here, the members that I've just created, and I'm going to go to node element, translate element, and I'm going to translate them by 4 feet in the gravity direction, and I'm going to click apply, and here you can see they have been created. The new elements have been created, and to these elements I have to specify the cross section as angle section. So I select them and I drag and drop the angle section. So the angle section has been defined, and now I need to create more elements, the cross bracing, the K bracing. So I select the cross section and I create the bracing. Midas Civil can automatically snap onto the center of the element, so you are covered with that. You don't have to worry about it. So the span at the middle of the element can be done automatically by Midas. You are covered with it. Now there is one catch here. The catch is this node the one that I have highlighted, and this node, the one that I highlighted right now, they belong to the same web. And since we are doing the grillage modeling, they are not connected to each other. And how do we connect them? So here we use the elastic link. We use the rigid type of elastic link, and we connect these two nodes together. Similarly, these two, and these two. So this way the cross frame has been created at one location. Now I'm going to copy this cross frame and I'm going to create more cross frames. So how do I do it? I go to node element, rotate, and I'm going to rotate it by a certain distance. So the distance between two cross frame is 15 degrees. So the angle would be this divided by 10, because there are 10 cross frames in span 1. So I'm going to specify number of times as 22 because there are 10 cross frames in span 1 and 12 in span 2. And I'm going to specify the angle, and I'm going to specify the radius. I check on intercept node element, and I also check on copy node attributes and element attributes. It's going to copy the rigid links too. And when I click on apply, you can see here that all the cross frames have been created, and you can also see that the elastic links are copied along with them. So this is how you easily model the entire superstructure of this bridge. Now let's complete the bridge modeling by modeling the cross frame. And how do we do it? First, let me zoom in at this location. I go to node element, create element, and I create, first I need the concrete material, so I go to concrete, ASTM reinforced concrete, grade C4000. I select the concrete material and the deck section, and I tap on 4 nodes and I create the deck section. Now once it is created, I'm gonna copy this deck section to other locations. And how do I do it? I'm gonna go to node element, rotate element, and once again I'm going to rotate it by, I forgot what the number of times was, so we easily get to know 50 here and 60 here, because here we are dividing it into 3 feet, so 50 times and 60 times, so it's going to be 110. So I'm gonna go number of times as 110. Angle of rotation, which we already computed in the Excel sheet. This is the angle of rotation, minus 0.13, and I put in here, okay, and I define the center distance. I check on intercept node element and I click on apply, and all the cross members are created. So this is how you create the cross members in Midas Civil for a curved bridge. So I have shown you the modeling of this entire superstructure. You just have to be a little cautious about what type of modeling scheme are you using here. And I think extrude is one of the best approach of modeling a curved bridge if you have a radius and the arc length, but you can also use the create element on curve. Now let's go ahead and model the boundaries. So right now we have modeled the links, but we have not modeled the actual translation support. So we go to boundary, define support. I define the support at abutment 1. I select the nodes. I restrain it at dx, dy, dz. Then abutment 2 and abutment 3. Now some of you must be thinking that it's a curved bridge, so at abutment 3 location we need the node local axis, and you guys are right, we do need node local axis here, but because we are running out of time here, I'm just gonna leave it for the moment. But yes, we do need node local axis at that location. Now let's go ahead and define the loads. I'm going to define 2 type of loads in front of you, self-weight and barrier load. So self-weight, I go to static load cases, I define the self-weight, dead load type, click on add, and barrier load, which is again a self-weight load or the dead load, so I created it as dead load. So right now I just gave it a name. Now I'm going to tell the program put the self-weight in the self-weight load case. So I go to self-weight button here. I specify the self-weight in the direction of gravity, factor as -1. Click on add, and the self-weight is defined. For the barrier load, I'm going to specify the barrier load on the edge girders only. So I go to load, element beam loads. I select the barrier load. So once again, the element beam load function is the one that you would be using for barriers. And I'm going to specify the barrier load, whatever barrier load is. And now to select the curved element, either you can select them one by one, or we have this option, select by polygon. It's a very nice feature for curved bridges. You can select the entire girder in one go. Check on the eccentricity because the load will be a little eccentric by 2 feet, and I click on apply. The eccentric load is applied on that girder, and then on the other girder, once again I need to select the other girder. So I'm selecting the other girder and it's selected. This time eccentricity would be negative, and I click on apply, and this way the barrier load has been defined. Now let's go ahead and define the moving load. To define the moving loads in a straight bridge, it's a very simple process, but in a curved bridge it's a little complicated. So let me show it to you. So I go to moving load, and I go to moving load code as #to LRFT, and I'm going to define traffic line lanes here. I click on add, and I give it name lane 1. The most important thing that you have to consider here is that the vehicular load distribution should be cross beam when you are doing the grillage model, because the cross beam would first transfer the load from the deck to the girder. And if you want to see the description of this item, just press F1 from your computer, and it's gonna open the particular help file for you. And this help file has a very nice description of how this type of loading is applied. So let me just quickly show it to you here. So I just pressed F1 and it opens the help file of Midas for me. So if you go down, you can see how the vehicular load distribution is done when you select the lane element or when you select the cross beam. So when you select the cross beam, basically the program will apply the load on the cross frame, and it's going to transfer it to the surrounding girders. And this way it is a much better distribution when we are doing when we are modeling the grillage. So to define the lane, I need to know what is the cross beam. So how do we define the cross beam? So we go to the group, we go to structure group, we right click, go to new, and we name it as, let's say, deck. I go to the workstream one more time, I double click on the deck section, I go to group again, and I drag and drop the deck section onto it. So this is how we have told the program where the deck is. So I go to traffic line lanes, I click on add, and I, let's say, name it as lane 1. And I want to define it on the cross beam. For the deck, I can specify the start and the end skew. Now if it were a straight bridge, I would have clicked on 2 points and defined a straight lane, but it's not a straight bridge. So I go to the number type and I select girder number 2 this time. To select girder number 2, once again I'm using the polygon selection feature. So I'm going to select girder number 2 like this, and once you select it, you copy the element number from the element numbers which are selected. So you go here, you select it, you press Ctrl C, you put the number here, click on add, and before you press OK, you need to tell the program the start span. So the start span, you will get to know, you can check on the the element number from here, and you will know where the 2 different span starts. The first span starts from span 3, and the second span starts from element number 383, I'm sorry. So you check them both on and click OK, lane 1 is defined. Similarly, let's define lane 2 quickly. So once again, I'm gonna select the lane 2 girders. I select this number here. I put in here, click on add, and check on the start span for span 1 and span 2, and this way I have defined two different lanes. Once the lanes are defined, go to vehicle definition. You can define either standard vehicles or non-standard vehicles. I'm defining the dynamic allowance as 33%. Similarly, I'm defining the tandem with dynamic allowance of 33%. So right now we have two different vehicles. Now I want to tell the program that either of them can give the maximum bending moment. And how do I tell it? I go to the vehicle class, I click on add, I select these two trucks together, truck and tandem together, and I name it as HL93. So this way the vehicle is defined, and now we combine the vehicle with the moving load case and the lane. We go to moving load case, we click on add, we give it a name, let's say moving. I go to add in the subload cases and we select lane 1 and lane 2. The maximum number of loaded lanes as 2. Press OK. Press OK one more time, and the moving load case is defined. Now there is one thing I want to tell you. AASHTO says that at the location of mid supports we need to consider two trucks each having the weight of 90%. How do we consider it? We have to check on this option, lane support negative moment, and then we tell the program the girder group. Right now I do not have any girder group. How do I create the girder group? I go back, double click on the composite section, go to groups, right click in the structure group, name it as girders, and drag and drop the girders. And I go to lane support negative moment. I tell the program that the girders should be considered when two trucks are considered with the 90% load at the location of negative bending moment. So this is all in all the modeling. It finishes the modeling of the superstructure. We can also model the substructure in Midas Civil, but we are going to have more training sessions in which we are going to talk about the substructure modeling too. So we are going to skip it at the moment. Now let's go to the analysis part and obtain the results from this particular bridge model. To perform the analysis, you will go to analysis, perform analysis. The program will perform analysis for you. In this particular model, I have already performed the analysis. It takes about 60 seconds, but I don't want, every minute is precious, so I just skipped it. I just want to show you the results. So to obtain the results, go to the results tab. Let's say I want to obtain the bending moment diagram. I go to forces, bending moment diagram, and I go to self weight, click apply, and it's gonna show me the self weight. If I want to obtain what is the value at different location, I can check on the legend and it shows me how the self weight bending moment looks like. Also you can change how the view should be. You can go to solid fill, and this is how it shows you how the bending moment looks like. If I want to obtain tabular result, I can click on this button and I can ask the program to give me the bending moment, shear force diagram, and stuff like that in the tabular format, and I can copy it to Excel. Similarly, I can obtain the envelope results for moving loads. I can go to MV max moving and I can click on apply. It's going to show me the maximum sagging bending moment for the entire bridge. To obtain the maximum hogging bending moment, go to MV min. It's going to give you the maximum hogging bending moment at the mid supports. If you want to obtain the results in the cross frames, what I can do is I can just check on the cross frames. So I just select the cross frame elements. I go to view active, or the shortcut is here. So it shows me all the cross frame elements. I go to result, forces, beam diagrams, and I obtain the axial force due to cross frame. I click on OK. It shows me the axial force due to cross frame. So similarly you can obtain it for different loads. Let's obtain it for self weight. This is how it looks like. Similarly for moving load, MV max, maximum compression, MV min, maximum tension. It's gonna show it to you. Let's just activate everything one more time. Now let's say I want to verify what is the what is the location of the truck to obtain maximum bending moment on a particular element. For that, you can go to moving load tracer, beam forces moment, find the girder on which you want to obtain the location of the truck for maximum bending moment, and check on apply, and it shows you the location of the truck for the maximum bending moment. You can also obtain the shear force, stress, etc., and you can obtain the location of the truck, and then you can change this to a static file, this load to a static file by clicking on this option. If I want to obtain what is the location of the truck for the maximum hogging bending moment in this on this girder, I can click apply, and since let it appear, so this particular girder, it is at the negative bending moment region, so the program takes into account 2 trucks and 90% weight of 2 trucks. So this is how you can obtain the results from Midas Civil. If I want to obtain reaction, go to reaction forces, click on apply, and it shows you the reactions. Let's say for sulfate, check on values, apply, it shows you the reaction. Similarly, if you want to obtain shear force, go to forces, beam diagrams, Fz is the shear force, click on apply, it's gonna give you the shear force like this. So this is how Midas helps you to obtain the results, and you can use these results to perform the design check and you know, do the load rating and stuff like that. So this is a simple training, and I believe after this training you would have an idea about how a bridge should be modeled in Midas Civil. And I think one of my friends working here, he has been giving you the answers, so I guess all the questions have been answered. But what I'm going to do here is I'm going to put my name and my contact details on the screen, so that if you have any questions or any concerns, you can call me. So this is my phone number, and my name is Nithal Malguri. One more time, my email is nmalguri@midasit or midasuser.com. This is my phone number. You can call me anytime you feel like, when you have any question for Midas Civil. Okay, so there are certain questions. The question is, can we get a digital copy of the PowerPoint presentation? Yes, you can get a digital copy of the PowerPoint presentation. And there is one question by Mr. Ved Sharma. The question is, how do you input different element releases for continuity at peer support for live load only? Well, Ved, we have already talked about it. You can use beam and releases for that. So we did discuss it in detail. You can use beam and release, and you can tell the program that for dead loads just use simply supported, and for live loads use continuous nature. So this is all from my side, guys. Thanks a lot for being in the webinar, for being in the training. I can see that more than 200 engineers were with us today throughout the training, which is a good number, and this shows that we are growing in this part of the world. As I know you guys are already familiar that in the Far East we are the software that every structural engineer uses. So please recommend our software to your friends and other engineers working with you, and we are always here to help them out in finite element analysis. So with this, I'm gonna end the session from here. If you have more questions, more detailed questions, you can you can send me the emails or call